Welcome to one of the most fascinating and stubborn mysteries in nanoscience, the quantum dot blinking paradox. Today we're going to explore why these tiny semiconductor crystals flicker like cosmic fireflies, defying our attempts at complete explanation. Before we dive into the blinking mystery, let's understand what quantum dots actually are. Quantum dots are semiconductor nanocrystals, typically 2 to 10 nanometers in diameter. That's about 50 atoms across, incredibly tiny. At this scale, quantum mechanics dominates. The electrons are confined in all 3 dimensions, creating discrete energy levels, much like an artificial atom. Here's a simplified representation. Imagine a cadmium selenide core with a shell structure. The quantum confinement creates discrete energy levels. When you shine light on a quantum dot, it absorbs photons, exciting electrons to higher energy states. When these electrons relax back down, they emit light at very specific wavelengths determined by the quantum dot size. Now here's where things get weird. Under continuous illumination, quantum dots don't emit light steadily. Instead, they blink on and off randomly. This diagram shows a typical blinking pattern. The quantum dot emits light for a while, then suddenly goes dark for an unpredictable duration, then lights up again. This is called intermittency, or blinking. Here's why it's a paradox. The illumination is perfectly steady, the temperature is constant, nothing in the environment is changing, yet the quantum dot randomly switches itself on and off. It's as if it has a mind of its own. What makes this even more mysterious is that the on and off times follow power law distributions, rather than the exponential distributions you'd expect from simple rate processes. So let's ask the critical question. Why do quantum dots blink? What physical mechanism causes this bizarre behavior? The honest answer is, we don't completely know. Despite decades of research, there's no single unified theory that explains all aspects of blinking. Instead, we have dozens of models, each capturing pieces of the puzzle. The most widely accepted explanation is the charging model, first proposed in the late 1990s. The basic idea is that a quantum dot can exist in either a charged state or a neutral state. When neutral, it emits light normally. When charged, the emission is quenched. Here's the picture. In the neutral state, the quantum dot emits light brightly. But if it becomes charged through ionization, gaining or losing an electron, it enters a dark state. But why does charging turn off the light? The answer is Auger Recombination. When the quantum dot is charged, an extra charge carrier is present. This allows non-radiative energy transfer. In the Auger process, instead of emitting a photon, the excitation energy is transferred to the extra charge carrier, which then dissipates the energy as heat. No light comes out. The Auger recombination rate is incredibly fast, ranging from 10 to the 9 to 10 to the 11 per second. This means charged quantum dots are effectively dark. Now let's address one of the most puzzling aspects, the power law statistics of blinking. Experiments show that both the on-time and off-time durations follow power law distributions. This is extremely unusual. The probability distribution goes as t to the negative alpha, where alpha is typically between 1.5 and 2.5. This power law means there's no characteristic timescale. What does this mean practically? It means that very long on or off events, though rare, are much more probable than you would expect from exponential statistics. The quantum dot can stay dark for seconds, minutes, or even hours. Here's a great question. Why power laws? In most physical processes, like radioactive decay, we see exponential distributions. Why are quantum dots different? The answer involves multiple competing pathways with distributed energy barriers. Imagine not just one way to ionize or neutralize, but many different pathways, each with its own activation energy. Imagine a landscape of energy barriers. Some are low, some are high. Electrons can tunnel through or hop over these barriers. The distribution of barrier heights leads to the power law behavior. One specific model that generates power laws is the diffusion-controlled electron transfer model. The idea is that charge carriers diffuse through the surrounding matrix to trap states located at various distances from the quantum dot. The diffusion time depends on distance. Diffusion timescales as distance squared. If trap states are distributed randomly in 3 dimensions, this naturally gives rise to power law statistics. Another important model is the distributed kinetics model, which focuses on the quantum dot surface. The surface of a quantum dot is never perfect. It has defects, dangling bonds, and impurities. These create surface states that can trap charges with a wide distribution of binding energies. The rate of charge escape from a trap depends exponentially on the barrier height E, according to Arrhenius law. K equals K0 times e to the negative e over kBt. If the barrier heights E are distributed over a wide range, then the escape rates K are also distributed. This distribution of rates produces power law blinking statistics. Let's work through some typical numbers to make this concrete. Consider a cadmium selenide quantum dot with diameter approximately 5 nanometers. Its radiative lifetime is about 20 nanoseconds. This is how long it takes to emit a photon when in the bright state. The Auger recombination rate in the charged state is about 10 to the 10 per second, or 100 picoseconds. The quantum yield in the charged state is the ratio of radiative rate to total rate. With Auger dominating, it drops to about 0.05%, essentially dark. The ionization rate, which controls switching from on to off, can vary from microseconds to hours, depending on the environment and surface chemistry. More recent work has revealed that blinking isn't just about single charge carriers. Multiple carriers can be involved. Under intense illumination, quantum dots can accumulate multiple charges. This creates even more complex blinking patterns with intermediate gray states. Here's a spectrum of states, from bright neutral to dim singly charged, to very dim doubly charged, to completely dark. The Auger efficiency increases with each added charge. Temperature plays a crucial role in quantum dot blinking, and studying it reveals important clues. As you increase temperature, the blinking becomes faster. Both on and off events get shorter on average. This suggests thermally activated processes are involved. The rate depends on temperature through the Boltzmann factor. K is proportional to E to the negative activation energy over kBt. Interestingly, at very low temperatures near liquid helium, some quantum dots stop blinking entirely. They freeze in either the on or off state. This tells us that thermal fluctuations drive the switching. One of the most important factors in blinking is surface chemistry. The surface is where the action happens. Growing a shell of a wider bandgap material around the quantum dot core reduces blinking dramatically. For example, coating cadmium selenide with zinc sulfide can suppress blinking. Why does this work? The shell passivates surface trap states, making it harder for charges to escape to the environment. It creates a barrier that confines the charge carriers. The confinement energy scales inversely with diameter squared. A thick shell increases the effective confinement, reducing the probability of charge ejection. In recent years, there have been breakthroughs in creating non-blinking quantum dots. This has been a holy grail of the field. By using very thick shells, typically 10 to 20 monolayers, combined with careful surface engineering, researchers have created quantum dots that are continuously bright for hours. These are called giant quantum dots, or GQDs. They maintain nearly 100% quantum yield without blinking. This has huge implications for applications. You might wonder, why does all this matter? Why do we care so much about quantum dot blinking? In biological imaging, quantum dots are used to track individual proteins or receptors inside living cells. If they blink, you lose track of your target. Non-blinking dots revolutionize this application. For display technologies like QLED TVs, you want every quantum dot emitting steadily. Blinking would cause flickering and uneven brightness. Understanding and controlling blinking is crucial for commercialization. For quantum computing and quantum cryptography, quantum dots can serve as single-photon sources. Blinking is problematic because you need reliable, on-demand photon emission. Non-blinking dots are essential. Let's look at a key equation that governs when a quantum dot will get charged. The charging energy is the energy required to add one electron to a quantum dot. It equals E squared over 4 pi epsilon 0 epsilon r times radius. Let's plug in numbers. For a 5 nanometer quantum dot, radius is 2.5 nanometers. The relative permittivity epsilon r is about 6 for typical semiconductors. Calculating, we get E squared is 1.6 times 10 to the negative 19 coulomb squared. The denominator includes epsilon 0, 8.85 times 10 to the negative 12, epsilon r of 6, and radius 2.5 times 10 to the negative 9 meters. This gives about 0.15 electron volts, or equivalent to 1700 Kelvin in temperature units. This is huge compared to room temperature thermal energy of 0.025 electron volts. This large charging energy means the neutral state is strongly preferred thermally. Ionization requires overcoming this barrier, which explains why charged states are metastable. Now let's address why this paradox remains unsolved, despite decades of research. Since blinking was first observed in the 1990s, more than 30 different models have been proposed. Each explains certain aspects, but fails on others. Some models emphasize charge transfer to the environment. Others focus on energy transfer processes within the quantum dots. Both seem to play roles. The local environment around each quantum dot matters enormously. Nearby impurities, defects in interfaces, all affect blinking. But these are nearly impossible to characterize and control perfectly. To make things more complicated, different materials show different blinking statistics. Cadmium selenide, indium phosphide, and perovskite quantum dots all blink differently, suggesting material-specific mechanisms. Let me give you an analogy to understand why blinking is so hard to model completely. Predicting weather is hard because it depends on countless variables: temperature, pressure, humidity, wind patterns, all interacting non-linearly across different scales. Quantum dot blinking is similar. It depends on surface chemistry, charge carrier dynamics, phonon interactions, coupling to the environment, all happening simultaneously across timescales, from femtoseconds to hours. Just like we can predict general weather patterns but not exactly when it will rain at your house, we can predict blinking statistics but not when a specific quantum dot will turn off. Let me describe one specific model in detail, the B-to-A transition model. Some quantum dots can exist in multiple emissive configurations called A and B states. These might correspond to different charge configurations or different surface states. The quantum dot can transition from the bright B state to the dim or dark A state with rate kBA. And it can transition back from A to B with rate KAB. If both rates are slow, meaning transitions happen on second-to-minute timescales, and if they vary due to environmental fluctuations, we observe blinking. One powerful experimental technique to study blinking is measuring the photon correlation function. The second-order correlation function G2 of tau equals the average of intensity at time t times intensity at time t plus tau, divided by the square of average intensity. This function tells you how likely it is to detect two photons separated by a time interval tau. For a perfect steady emitter, G2 of tau equals 1 for all tau. For blinking quantum dots, G2 of tau becomes much greater than 1 at long time delays. This is called photon bunching and directly reflects the power law statistics of blinking. Interestingly, there's a connection to the quantum Zeno effect, a fundamental principle in quantum mechanics. The quantum Zeno effect says that continuously observing a quantum system can freeze its evolution. Frequent measurements prevent transitions between states. Some researchers have proposed that very intense illumination might suppress certain blinking transitions through a Zeno-like mechanism. The constant excitation prevents the quantum dot from relaxing into trap states. However, this interpretation is controversial and still actively debated. It's another example of how quantum mechanics intersects with nanoscale phenomena in surprising ways. Despite our incomplete understanding, researchers have developed practical strategies to control blinking. Strategy 1 is thick shell growth. By coating the quantum dot with many layers of a wider bandgap material, you confine the charge carriers and reduce trap state coupling. Strategy 2 is ligand engineering. The organic molecules attached to the quantum dot surface can dramatically affect blinking. The right ligands passivate traps and stabilize the surface. Strategy 3 is matrix engineering. Embedding quantum dots in the right host material can minimize charge transfer pathways and stabilize emission. Strategy 4 is electrochemical gating. By applying an external voltage, you can electrochemically control the charge state and suppress certain blinking pathways. Beyond applications, the blinking paradox raises deep questions about fundamental physics at the nanoscale. Blinking reveals the extraordinary complexity of single-particle quantum systems. Even a simple nanocrystal displays behavior we can't fully predict or control. It demonstrates how quantum and classical worlds intersect. The blinking involves quantum charge states, quantum energy levels, but also classical diffusion, thermal activation, and environmental coupling. The power law statistics challenge our understanding of non-equilibrium statistical mechanics. Why do these systems exhibit scale-free behavior? What does this tell us about the energy landscape? Let me highlight some current research frontiers in quantum dot blinking. Researchers are using advanced single-dot spectroscopy with femtosecond time resolution to watch blinking events happen in real time, revealing the ultra-fast dynamics. Machine learning algorithms are being trained to predict blinking behavior from structural and chemical information about the quantum dot and its environment. Quantum simulations on supercomputers are modeling the many-body effects involving hundreds of atoms, phonons, and charge carriers to understand the collective behavior. New materials, especially perovskite quantum dots, show unique blinking signatures that may reveal new mechanisms and help us understand the universality or material specificity of blinking. Despite all this progress, many fundamental questions remain unanswered. Is there a single universal mechanism underlying all quantum dot blinking, or are there fundamentally different types of blinking with different origins? We observe power laws, but why exactly do they emerge from the microscopic quantum dynamics? What is the deep connection between the quantum dot energy landscape and the macroscopic statistics? Can we ever predict when an individual quantum dot will blink? Or is there fundamental unpredictability, perhaps related to quantum measurement backaction? How does quantum dot blinking relate to similar intermittency observed in single-molecule catalysis, enzyme reactions, and other nanoscale systems? Is there a universal framework? Let me summarize this fascinating paradox. Quantum dots exhibit unpredictable blinking between bright and dark states under constant illumination, following power law statistics. We understand that charging causes the dark state through Auger recombination, which is incredibly efficient and non-radiative. Multiple mechanisms contribute to the switching dynamics, including charge diffusion, trap state distributions, and surface chemistry fluctuations. Despite dozens of models, no single theory captures all aspects of blinking across different materials, environments, and timescales. This is why it remains a paradox. Practical progress in suppressing blinking through thick shells and surface engineering has enabled applications even while fundamental understanding remains incomplete. Ultimately, the blinking paradox reveals the profound complexity that emerges when quantum systems interact with their environment at the nanoscale. It's a beautiful reminder that even simple-seeming systems can harbor deep mysteries.